Yes, let us talk about in the last class. Okay. Yeah, yesterday we were talking about of the PSK modulation techniques. Okay, exactly. DSP modulation techniques. I have mentioned it. PSK modulation techniques is the one. Look back. This is the information, and this has to be in polar. Very important point is this is to be polar baseband signal, right? And this is the information which you are going to keep. This is the information which we're going to keep. Depending upon the information of the carrier wave, we'll change the frequency. Look back, the frequency of this will be frequency of the one. Okay, is this frequency? The phase, sorry, phase of the for the bit is get changes as soon as the bit there is a transition from 1 to 0, then there is exactly this. So whenever the bit changes from 1 to 0, 0 to 1, phase shift will be changed. Phase of the carrier will be changed. In other words, we can say that the information to be passed, that is the polar in the form of the binary sequence pulses, absolutely in the what we call carrier wave. Look back, this carrier. That means we are coding the information to be passed. We are protecting within the envelope of the carrier wave in the form of what exactly the phases. See S1 of 2, S1 of 2. Let us say this is exactly transfer the this is S1 of t transfer the signal to represented 1 in BPSK of this part like this BPSK, and signal to represent 0 in BPSK. This is the signal which represents the 0 of this signal, which is absolutely here, because look back here, 2 pi fct plus y. This is the phase of the signal represented 0 has to be different of that. So that is why cos 2 pi ct plus pi is 1. So look back, this is S1 2, S1 of 2, it represents the passing of this one bit in a BSK, which is exactly coded in this form of this. In a similarly, what exactly here and there. Okay. Okay, exactly. TB is equal to bit duration. EP is equal to transmitted signal per energy bit. This is EP. This is the energy of the magnitude. See, look back what exactly I told you. Whenever you transfer the signals, especially in the AGWG signal, it must consist of a basis function and it consists of the magnitude. Magnitude is most of the important. The basis functions will be consist of the information about the kind of the base phases, frequencies of the carrier wave which is used to product the information. That is the energy, which is this part especially. That is EP and TB, this part. So look back here. Again, see, I mentioned it. This is this two S1 of 2, S2 of S1 of S1 of 2 and S2 of 2 is called as an antipodal signal. Since okay, exactly since okay, this is look back. I told you this energy of the signal and the phase magnitude of the signal has to be the part of product of the signal is S1 of 2 is equal to energy of the signal and phase of the signal. So this is energy. This is the signal S1 for transmitting the message 1. This is the signal transmitting the message 0. This is energy of the signal, and absolutely this is phase of the signal. So when you say the signal SI of t is equal to energy of the signal and basis function phi of t. When you compare with this function, we can get what is exactly the base of this basis function. That is a phi 1, which is a part which will be multiplied to the signal before sending the message to the transmitting message, which was very clearly told in the chapter number 2. That is absolutely geometric representation of the signal. So any signal will be consist of energy of the signal and basis function. So energy of the signal is the basis function is basically indicates about phase, frequency, all other matter. So which will be used by the receiver to predicate what is the magnitude, that is energy of the signal at the receiver. Okay, so that means when you compare with the basic definition of this and this, we are able to see phi 1 2 phi 2 exactly like this. Okay, so look back. So that means we can write S1 of 2. We are going to represent represent the signal passing the bit 1. okay, within the time duration d, S2 of 2 is equal to minus of EB minus square root of EB into phi 2 0 less than RT and TB of this. So now, which see, basically these are the signal which absolutely sending from the BPSK transmitter to the channel. Okay, now exactly I told you that. So the receiver has to identify the signal S1 of 2 EB. That is, if S1 of 2 is indicating for, it has to deduct the magnitude of the S1 of 2 to see that whether the received signal is 1, because since S1 of 2 is always represent 1, S2 of 2 is always represent the what 2 with the basis function phi of 2 for S basis function phi 1 for S1 of 2, it represent the this thing what I call 1. So now how we exactly identify? By drawing what I call signals in the absolute in the signal space. Look back in the signal space here, there are one functions here. Look back, this is the decision boundary, one function. Look back here, when you say this is square root of EB minus square root of EB, let us say this is a phi function, phi 1 function, the magnitude, this is the message point, okay, exactly. EB of the signal is here, the minus square root of EB absolute of S2 is here. See, exactly this is S2 of 2 phi 2, S1 of 2 is a phi, exactly like this. This is phi 1 and phi 2. Look back, this is the signal which is going to transfer from the transmitter of the BSK to the BPSK receiver, okay, via channel. This will be identified by the receiver by plotting in the signal space whether the received information in bit or 1. How we are going to plot? This will have basis function phi 1, okay, exactly, decision there. The message point is 1 here, that is a transmitted message point 1 is equal to square root of EB, message point 2 is equal to minus. Look back, this is the signal will come in the region 1, and this is the signal will come in the what, region 2. This has to be mentioned that, okay. I hope. Let's look back. As for the function, we have one basis function and two message M2, therefore we require one dimensional signal space for representing S1 to N is equal to 1, M is equal to 2 signal. That is exactly this, okay. Right. So this is the what, how the BSK generation goes, BPSK receiver goes, and as you know that signal absolutely SI of j is equal to 0 and all these things. So this is Sij, S1 of 2, pi 1 of 2, okay, exactly. See, first signal, see, look back here. The first signal basis function 5, because basis function 1, whether the received signal is 1 is this, whether the received signal is 0 with the basis function 1 minus 1, okay. Look back how the generation goes. Simple aspect, as I mentioned it. First thing is binary data. This has to be what? But I mentioned it exactly. This is has to be polar Z square, polar sequence signal like this, and product pi 1 2 is multiplier. That is basis function has to, this energy of the signal has to be multiplied by 1 before transmitting the message. This will be used by the receiver at the receiver to predicate. That's what we are going to multiply the signal, that is a magnitude, the energy of the signal 512 of this. That is exactly we call it as binary. The output is, this is binary. This is exactly called as BPSK. By block diagram of PSK transmitter is this much. The generate, see, this consists of this two blocks, polar NRZ level, because when you use a PSK, it has to be used polar, what you call it as, it has to use the what you call it as polar NRZ levels, so binary sequence. That is why the first block is polar NRZ. Whatever the frequency, whatever the signal to be transmitted 1001 will be converted into polar NRZ level line coding. Then it will be multiplied by the bias function, as we mentioned. The bias function will indicate the phase, frequency, and some other information from which the receiver will predicate the received information is distorted or corrupted, or that is the energy. There is a bit is 1 or zeros. Okay, exactly. Second is product multiplier. Now, what is exactly the BPSK coherent deduction? See, very important. BPSK, so look back, I mentioned is in BPSK, binary phase shift keys. 100 will be coded in the phase of this single carrier wave. That means we need to deduct this carrier magnitude to identify the received bit is 1 or not. That is why by checking the envelope of the magnitude of the envelope of the transmitted signal at the receiver, whether it is a 1 or by envelope signal, That is why we call it as coherent. That means in coherent, we are taking one signal. At each point, we'll exactly identify the magnitude along with the basis, whether it is 1 or 0, and according to which the receiver will identify 1 with the help of the basis. That is why it's coherent. It will check point by point of the received signal, and hence it is called as a coherent deductions. Okay, so non-coherent, yes, is possible. In generally, that is a different. We'll go right now. The BPSK is always a coherent because it's whatever the received signal in the form of analog, that is BPSK at the receiver will have one magnitude of the signal. At each point, the magnitude of the signal will identify, but the information received is 1 or 0s. Okay, that is why we have BPSK as a coherent deduction. Okay, right? See, coherent deduction is what exactly? The coherent deduction is consists of correlator. Next is what we call decision devices and with decision. What is exactly the coherent correlator here? Look back here, as I mentioned, is x of this is, let us say, x of t is the received information at the this whole block is exactly receiver. Then I told you that this will be have something basis function. Whatever the received information will be multiplied by the what exactly the basis function, and it will be integrated over a time period because signal will be changed during the time bit duration TB. That is why we are used, look back, 0 to TB. This is exact. That means we're making the necessary information, necessary requirement to analyze the received input at this with the help of the what. This is exactly called basis function, and this will multiply for the time duration. So whatever the signal will come in this form of x1. Now this x1 we need to deduct whether the received information is bit is 1 or 0. What will happen? The decision device is simple electronic circuit. What will happen? It holds the maximum voltage, threshold voltage is exactly 0. That means whatever this x1 will be compared with threshold voltage and it take a decision. For example, threshold voltage, if this is greater than 1, it means that if x1 is greater than 0, it means possible is 1 because we are sending the information either 0 or it may be even some kind it's corrupted because there is no digit or integer part of. If it is x1 is greater than 0, then automatically the decision device, the received bit is what you call as a 1 and received bit is equal to 0 if x1 is less than that. So I hope this is what exactly the block diagram of the BPSK coherent deduction. In this point, you have to mention why it is coherent, because coherent, why cannot be coherent, or why cannot be non-coherent, and why is a coherent. There's one more most important which I mentioned. How this process, as soon as the signal come, it will be multiplied as a basis function, and it will be what I call integrated over 0 to t x1, and this threshold voltage decision will be taken. Okay. Now look back. So now what exactly is this is exact. Now how the decision, how the signal, because as I mentioned it in a geometrical signal space, that once the signal is received, exactly that signal will be what will happen, will be making the signal space. Let us take now, say these are the, say observation vector is exactly received input here. Then now the following decision rule applying in the signal space of coherent deduction. The observation exactly vector is equal to received input at the receiver lies in the region of Z1 if L of Mk is minimum, K is equal to 1. This is exactly the one decision rule. This is a decision rule we absolutely I mentioned in likelihood in the chapter. Okay. If any functions received, any received function, that is a received bit, should be lies within the expected region. So the transmitted message is same as that of the transmitted bit at the transmitter. So that means that for that condition, the observation vector, look by capital X, received input the received lies in the region of Z1 if L of K is M is equal to K. Let us assume that, so XCT consists of two signals. Whatever the information comes, absolutely it will consist of S1 of 2 and S2 of 2. S1 of 2, let us say, represents 1, which is absolutely has to be positive pulse phase, as we assume, a integration of what we call square root of EB into 5 and 2, and for S2 is the exactly, it has to be what? Minus here, look back, very important, minus square root of EB into phi 2. That means whatever the phases of the received signal S1 with a phase, with a bit 1, S2 of 2 is equal to bit 0, right? This is exactly the message. This is, we know how the, okay, exactly here, right? This is absolutely the receive this. This is exactly the signal space as I mentioned. The region, first region, the set of point close to the point 1 called plus B. The set of points close to the point is minus B. Now the only thing is what, once the signal come, after multiple base function. Then x of once this decision devices will make this decision devices will compare with the threshold I mentioned it. If this is the bit received as an input at the receipt, if it is less greater than 0, then we conclude. That means this decision will be go, whatever the input will be, input will be drawn in the signal space within the signal space of the characteristics and decide whether that received input, that is x1, is belong to plus EB or it minus B. Depending upon that, one decision will be taken. That is, this is the point. Look back to decide this, the signal S1 of the binary was transmitted if the received signal point falls in the region. That to decide the signal S of 2, the binary signal chip was transmitted if the received signal point falls in the region. That is what the decision make. In generally we say threshold voltage 0. That kind of action comparison will take place by plotting the signal in the device in the signal space by itself. Understand mathematically is this mathematically okay. This is absolutely lies in the whatever the transmit the reason 1 or reason 2. For example, S1 is lies in the reason 2. It means that even the transmitted message is a 1, but it falls in the reason 2. It means that the received message 0. There is a kind of distorted or a corruption has been occurred. So it will mention that. Okay, exactly like this. Right. So now we need to look back. So these are that means by looking the absolute, there are two kind. There are for two possible. There are that means exactly we can say by looking the BPSK transmission, BPSK this thing, BPSK transmission, BPSK coherent. By looking block diagram, how the decisions take with the decision device of the binary reduction point of view. So we say that there are two possible. Even though received signal is 1, if it is lies in the region of S2, then we can say the received transmitted message is 1, but receiving message 0. What we call it as this kind of error. Possible one of the error is that is exactly called error of the first kind. This is exact error of the first kind. So now the second possible is that let us take S2 of 2 has been received at the transmitter. It means that even though if it is deducted as a 1, then we can say that it has deducted as a 1. But even though transmitted message is 0, we can say that there's a message received message is wrong. That is exactly we call as the error of the second one. So now let us say, so that means what should be the, if X1 is a received signal with the symbol 1, that is R1, let us say output, the received signal at the X1 is a received input signal, S1 of 2 is the transmitted message, the transmitter. Please don't try to confuse. Here, there's a book has been utilized. S is for a signal transmission. A capital X or a small x absolutely used for receivers. Let us say X1 is a received signal with a symbol which is equal to S1 of 2. That if you say S1 of S1, the X1, in order to predicate by the receiver is perfect, that is transmitted message as 1 has to be equal to the received message, that is a 1. If it is possible by using what exactly this condition, Z1 less than or 0 less than X1 of infinity. Okay. So now let's go. How exactly, what kind of the possibilities error functions? So that is exactly we call it a zero error probability. Okay, error of a probability. That means so far we are what is BSK? How the BSK generation goes? How the what is the BSK deduction? That is at the receiver. What we call coherent deduction from the devices. How the signals goes? How the decision will be takes when X1 is greater than threshold by plotting the signal in the space. What we call it in the signal space. Absolutely, it is finding whether there's a fall in within the perfect region of the condition of the transceiver of the transmitter, then we can say that absolutely is okay. Otherwise, there are two possible, first kind, second kind. Now the possible of error of probability error. Okay, exactly, error of the probability. So now look back, very important here. This is absolutely, now I'm talking about what kind of error probability. That means even though received message is 1, it may deduct as a 0. Even though it receives the message is 0, it may deduct as 1 by using the what you call signal space, that we call as error of probabilities. Okay, error of probability of deduction. So look back, what is the kind of that is what is the error of probability detected by the receiver? As per the AWG theory, the received signal mainly depends upon the probability function of the signal received, not in the noise. That's absolutely, it's very clear. We defined it in the signal space. whatever when you transmit the signal from the transmitter to the transmitter to the receiver via AWG channel, that means signal will not get corrupted by the signal, what you call noise. Okay, the mean of the signal at every point of the channel is only depend upon the signal, not on the noise. But variance of the variances in the channel, it mainly depends upon the noise, which we are very proved in the this signal, what I call AWGN theory. Okay, here also look back, since we are talking about of the AWGN theory, as for the AWGN channel theory, the received signal is mainly depends upon the probability density function of the signal, that is a receiver. That means it does not depend on the noise. We have proved it. Very important. That is why we have mentioned one of the basic advantage while using AWG channel in the transmission communication rather than any kind of a channel, even though it exists a lot of kind of, even though it exists, or it may give some of the advantage, maybe in terms of bandwidth, maybe in terms of the frequency, high frequency, maybe in terms of the SNR, whatever it may be. AWG is beautiful, one of the one which does not affect the signal as much as possible. That means it gives less energy, less noise, as less possible, absolutely in the channels. Okay, exactly. So that means that is what this, the conditional probability density function. That means you have to check out what conditional probability density function. As I know, when you say this is the signal will be transmitted AWG, when you say signal is transmitted AWG, the noise is always a random in nature, because even though we use, of course, we have mentioned it, the power spectral density of the noise in the AWG channel is a constant, but still it varies, because as we mentioned very clearly, there are very characteristics and primitive characteristics of the channel is that it get affected due to the external internal factor, which we have talked about in the first unit, first modulo. So that means that the probability function, that means what we are saying, when the signal is transmitting from the receiver to the receiver, transmitter to the receiver, what will happen? Signal is get, what I call it, a signal is absolutely get distorted or corrupted, even in AWG channel. That is has to be, that means we can say that noise function is a variance. That means noise function is a random variable. That means conditional probability function is receiving the information is a wrong at the receiver, which is not in accordance with the transmitted message at the transmitter. We can verify with the help of the, due to the noise has to be in a random in nature. Therefore, the probability density function which has to be analyzed with the what exactly random variable x1 given the symbol 0 was transmitted. Look back, the conditional probability density function is depends upon, that means it depends upon it depends upon the random variable. So we can say the conditional random density function with the random variable x1 is given by this, given the symbol 0 was transmitted, which is given by, see, look back, x1 is transmitted, the expectation is what exactly 0 was transmitted, but it may deduct exactly was maybe 1, that is exactly what error of probability. But conditional probability function, which is expectation that the received information is as same as that or the transmitted symbol, that is 0, f of x1, the probability density receiving is given by this formula. As I mentioned, this is absolutely what Gaussian is a Gaussian function, because AWG function max is according to Gaussian, and as for the signal will be multiplied with this function, because this probability density function absolutely mention is exactly minus. So this minus will be predicated the probability density function receiving the information at the receiver as same as that probably. In this case, capital X1, the random value is 0, is this function. Similarly, the condition variable, see, this is exactly at the time of the receiving. Similarly, the condition probability of the receiver decoding in favor of 1. So this is exactly 0, 1. Similarly, the conditional probability decoding in favor of a symbol 1, given that the symbol is 0 transmitted, P10 of this much. Okay, exactly. So this is absolutely this one equation exponential, but it is indicating absolutely this function is a probability density function. The probability, conditional probability is given is this much. Okay, with this symbol, given that symbol is 0, was damaged. That means P1 is 0. Look back. Even though the symbol is transmitted, 1 has come. This will be multiplied over exactly this, what I call this. So probability density function P10, that means the transmitted message is 0, but receiving is 1. This is transmitted message, this is receiving message, will be given the function of the error probability of detecting at the receiver due to the noise present in the channel, that is AWG, which is present in the channel, which is due to the what I call random in nature, accordingly which we are multiply with this. Accordingly, this is the equation is absolute. See, put it across, this is just putting across z equal to this function of this, okay, exactly. So by changing, for a mathematical purpose, we have put it across by changing the variable. So when I put across this for a mathematical purpose, I am getting the probability density function is transmitting the deduction as a 1, even though it transmitted as 0, which is absolutely given by this, okay, exactly, right? Right. So by this is, so just putting across, just because there is a quality function, absolutely, by statics theory, which is given by 1 minus f of x, which quality function q of x is just putting across to here. Okay, just substituting the previous equation, that is this equation, that is this equation. Okay, exactly. We'll get back to work. We'll get back to this equation, and right, so this equation will get back to this equation, substituting that. So that means they look back that therefore the conditional probability of the receiver deciding in favor of symbol 0 given the symbol is transmitted is opposite side of the signals with the 1. So that means absolute, look back here, the probability density, this is the equation 1 gives the conditional probability function of the error of the first gate. The equation, look back here, very clear. If this is P10 and 01 is what exactly? Transmitted message is 1, but receiving this is this. If this is lies in the one region and P10 lies in the what exactly? One region, P01 is also lies in other regions. Okay, exactly. This is what exactly we have mentioned. This is absolutely condition which I explained already. This, okay. So the P01, look back. Therefore, the P, if you say if you say P01 and P10, it has to be symmetric, because I mentioned is that P10, okay, P10 is equal to the received message is 1, but transmitted message is 0. P01 is received message is 0 and transmitted message is 1, which has to be opposite in nature. With when you say symmetric about of with respect to origin, which absolutely given, okay, exact that. So contain the same values. So that means P01 and P1 will the magnitude of the probability of error, which absolutely, which is given by P is equal to 01 is equal to what? Q to 2 into B. Look back. The probability depends upon the only two factor, energy of the signal EB. But here one important, N0. N0, I mentioned it. It is a power spectral density. Okay, power spectral density of the channels. Okay, exactly. So that means P01 is equal to Q into integral of, sorry, Q into square root of 2EB and not. So, okay. So when you take the average of the both, because P10, P01, both are the different way of probability by the receivers. So what is the maximum probability error? Taking the maximum probability error can make by a receiver taking the average of 0 P01 and P10. We'll get back to this. Average probability of a symbol error by the receiver is given by this equation. So from 3 we can conclude that it PE, that is a average probability of symbol error by the receiver, conclude that will be reduced as we increase the energy bit of the transmitted. Okay, okay. So look back. The probability error will be reduced. Look back here. As energy of the signal is more, that means let us say energy is equal to 4. Okay, exactly. Then this term is becomes what exactly less, because the EB within the square. That means as you increase the energy, the PE will become reduced. Then that means that the deduction of the received messages, that is a received symbol at the receiver, will be same, will be almost is equal to same as that much, or otherwise PE will be reduced as energy of the signal. Or in other words, we can say with respect to the signal system theory, the magnitude is strong, the information is also as strong. Okay, That means integral of minus into the plus infinity e square into dt, which is seen in signal theorem as a magnitude of the signal. Magnitude is indicated absolutely with concentration of the energy. If the energy of the signal is far, if the energy of the signal is more, then the probability of deducting the wrong answer by the receiver is 0. That is exactly. So to achieve, look back, to achieve this conditional probability, that means absolutely this is exactly, to achieve this condition, the message point corresponding symbol move further apart. That means what exactly? Look, this energy of the signal has to be more. That means energy signal is one with what I mean that energy is more mean frequency has to be more, because both are indicative of the frequency and time. So that means in order to achieve the more energy, so the P will be reduced, what exactly required, corresponding symbol 1 and 0 move further apart. Okay, that means that. So now the power spectra, exactly the power spectrum. So look back, the power spectrum binary PSK signal is this. See, look back, PSK, I told you that it uses only one carrier, changes the phase depending upon what exactly, depending upon the bit to be transmitted. The bit may be 1, and bit may be, bit 1 is equal to plus cos omega t, bit 0 is equal to 1. That means the phase of the phases of the bit transmitting transmitting the message, one should be close. The basis of the message should be one phase, and within that phase it will be changed if the transmitting message is equal to exactly 0. That is absolute. Okay, this is okay. Okay. So this is absolutely the magnitude of the signal is okay here. So here like that, minus omega c omega 2 and pi 1 of. See, this is, that means whatever the message we are doing will be within the phases of the carrier information, that is carrier information, the carrier frequency. That means the spectral magnitude of the signal is absolutely will exactly close here. So that means the above spectrum has been drawn with the equation, because as you know, S1 of t, that is the signal to be transmitted, is equal to energy of the magnitude and the basis function. Energy of the signal will be depend upon the what exactly root. Okay, root signal, and phi 1 is exactly mentioning what exactly frequency and phases of the signal, which absolutely how this is the signal which is absolutely given for S1, that is a signal to be transmitted for. This is very clear, which I mentioned. This is because signal energy, the phases will indicate phase, basis function will indicate the phase, and this. So what is exactly how this the signal will be what I call shape. This is actually given by gate shaping signal. Gate shaping signal. Gate shaping signal. The G of t is equal to 2 EB divided by ET, 0 less than or t less than 2B, 0 otherwise. Okay. So this is how exactly this goes. So this is absolute. The value of the spectral density is absolutely given by this. So this all be explained. G of t is equal to positive for one value to be transferred. G of t, that is the magnitude of the signal, or the power spectrum. If that is a pulse shaping of the power spectrum is equal to G of t is minus for 0, depends upon the value of the transmitted. The basic assumption mode in the digital communication that the incoming binary signals are random in nature, the symbol one or two being equally. Therefore, the binary symbol transmitted during the time slot being a statistically independent. Thus, the power spectral density depends upon the randomness. These are simple, which I explained already, because everything, whatever, even the signal transmitted from the, what you call it as signal is transmitted from the transmitter through the channel. Once it flows started into the channel, it is all dependent on the noise. Even though you have AWG noise, because noise will get some variation. That means the mean of the signal, even though it depends on the magnitude, but some kind of a signal noise will variation there. That is, even spectral density is also variation. Okay, exactly. So the value of the spectral density of the BPSK, that is given by this, and this is what exactly the functions. Okay, like. Okay, next, from this point of view, SBS is symmetric about the vertical axis. S2 of this, from just analyzing that fact as a simple matter of this, SBF, that is power spectral density of BPSK is depends upon the what? Symmetric about the vertical axis, SBT through 0 and at multiples of the bit rate, that is F is equal to 0, SBB of false of the inverse pair of the function, since S squared do BBF limited this. Oh, this is absolute. This is the value of consideration. So now timing is running off. So we'll do the next class. QPSK is another type of generic form of the BPSK. How it is different, but of course, whatever QPSK uses, The basic principle of the what exactly? Basic principle of BPSK, that is the one in order to transmit 1 and 0, it will use the phase of the carrier, but here in the QPSK, it uses the two signal for representing one signal for one phases of the one signal, let us say S1 to one signal, another signal S2 off to transmit the 0 with another phase which minus cos omega t. That is exactly the quadrature. Which since once you say sine cos omega ct for one signal for transmitting message 1 minus cos omega t another wave for other signal, that is another binary sequence, another carrier wave signal for transmitting the message 0. That means both are in anti nature, absolute, that is anti-phases, that is exactly 90-degree difference, minus cos omega t, I can write it as sin omega ct. So absolutely we can say that the two signals to be transmitted will be sent across in a different signals, rather than not, instead of sending as a one signal as in BPSK, here in a QPSK we are going to send a two signal, one signal representing the transmitting the message 1 with the carrier wave cos omega ct, and sending the message 0 with the different phases minus cos omega ct, that is exactly what sin omega ct. So that means we'll do the what is how the generation coherent deduction will take place in the quarter phase shift key in the next class. Okay, have a nice day. Thank you. Next class will be indicated